So the last thing from this section, the second to last lesson of the year, is how to find sums, exact sums of certain infinite series. So remember back from 9.1, we can find the sum of an infinite convergent geometric series. And the formula for that was first term over 1 minus r. And that's kind of what we've been working with here with 1 over 1 minus x. The other one, which is not a BC topic yet, but still pretty cool, is the telescoping series. If we expand out a sufficient number of terms, either by partial fraction decomposition, you'll have a fraction minus a fraction. Things can cancel, and then you're left with just a finite number of terms, which you can add together. The last way on the AP exam that you're expected to find true exact values, and not approximations, of infinite series are when they are any one of the 3 series or 4 series, really, that you memorize evaluated at an x. So remember, we memorize sine, we memorize cosine, we memorize d, and we memorize 1 over 1 minus x. So any of those could be evaluated at a specific value of x. So that's what example 13 is about. It says, by recognizing each series as a Taylor series evaluated at a particular value, find the actual sum of each of the following infinite convergent series. So 1 minus pi squared over 2 factorial plus pi fourths over 4 factorial, blah, blah, blah. Do you recognize the trend in that series as one of the ones we memorized? It looks a lot like cosine, right? It alternates, and it has even terms, right? Even powers. And remember, cosine was the even function, had y-axis symmetry. So this is essentially cosine, but it's not cosine of x, right? Because what we memorized was x squared over 2 factorial, x to the 4th over 4 factorial, x to the 6th over 6 factorial. So this is the cosine function evaluated at what? Pi, right? And since we recognize that now, we can evaluate cosine of pi rather than adding up all of these terms. We can just use the unit circle. What is cosine of pi? -1. Yeah. And that's the answer. If you were to type that into your calculator in sigma notation for like 9,999 terms, you get something really, really close to -1. So that's not that bad. All right, this one down here. Notice it doesn't alternate. There's only 2 that we memorize that don't alternate, e to the x and 1 over 1 minus x. And only one of those 2 has factorials in the bottom that match the powers in the numerator. And that's, of course, what? E, right. So e to the x would, of course, have 1 plus x squared over 2 factorial plus x cubed over 3 factorial. So this is not e to the x, but e to the what? ln of 4. Yeah. So once we recognize the e function evaluated at natural log of 4, we can evaluate this a different way, rather than adding up all these infinitely many terms. And of course, that equals 4. So this is a convergent series, and it converges to the sum of 4. And last but not least, this one alternates. And we only memorize 2 alternators, so it's got to be a sine or cosine. So if you look at the powers, they're odd, so this has to be sine, right? But it's a little bit different here. First of all, it's not just sine of x, because it's not just x cubed, x to the 5th, x to the 7th. So this is really sine of pi 6, but there's something else here. What else is this one? There's an extra factor of 2 in each and every term. So this would be equal to 2 sine of pi 6. Not sine of 2 times pi 6, but 2 times sine of pi 6. Yeah. So be careful. It's not always just going to be the actual function. It'll be recognizable. So they're not going to simplify each of these terms. They'll leave it in a recognizable format. So what is sine of pi 6? That's the cosine of pi 6. It's 1/2, yeah. And then, of course, half of 2 is 1. So this series, as complicated as it looks, does converge, and it converges to the number 1. So there you go. That concludes this section. And this section was pretty important, right? Recognizing geometric series can be a huge time saver in determining interval of convergence, radius of convergence, generating other series that are based on it, and of course here at the end, finding exact sums if it's not a geometric series or telescoping. Okay, any questions on this section? There's only one section left, and we'll save it for Wednesday. Okay?